Welcome back to Mrs. Schroeder's Chemistry Classroom. Today we're going to talk about Section 2.3, talking about these first two objectives, distinguishing between accuracy and precision. A couple quick definitions. Make sure you pause this, write this down. For example, if I take a 100-gram mass and I take it back to my scale and I put it on one of my scales back there, and the scale reads 99.9 grams. The scale is pretty accurate. Not perfect, but it's pretty accurate. If I weighed it again the next time, it might read 100.1 grams. And sometimes we see a fluctuation because the wind blows and it changes it a little bit. But it's pretty accurate, and it seems to be right around there. Now, if I say my scale is actually off and I don't know it, but I take my mass back there and I weigh it on my scale, and I didn't know that somebody dropped the scale or was playing with the scale and pushing on it or spilled some chemicals on it and did something, and I took my mass back there and I weighed it, and it was 89.5 grams. Okay, that didn't sound right. Maybe so I took it and I tried it again. The next time it was 89.6 grams. And I can try it as many times as I want, and it keeps showing 89.5, 89.6. That's a precise measurement, but not an accurate measurement. So this one is precise because they're close together, even if it's not the right answer. A lot of times we use a target to try to get the idea of what accuracy and precision mean. If I look at this first target right here, my target is the bullseye. I'm trying to shoot for the bullseye. If somebody's shooting at the bullseye and they hit where these blue dots are, is this accurate or precise? And the answer is neither. The shots are scattered all around and they're not close to the target. The second one down here, the yellow dots, I would call this one accurate because they're around the target, but they're not precise because they're kind of still scattered around. Now this target over here, you would call not accurate because they're not really close to the bullseye, but they are very precise. If this person just adjusted their aim, they become the red dots down here, which are accurate and precise. Okay, so that's the idea of accuracy and precision. Now in chemistry, it's important to select the right piece of equipment so that our measurements are the most precise and the most accurate that we possibly can get. This helps cut down in experimental errors. For example, if I was told you need to measure 5.5 mils, and I noticed this last week when you were in lab and you had to get 3 mils of vinegar, and some people came over with this one. Can you measure 3 mils in that very easily, or in this case 5.5 mils? Absolutely not. Okay, 3 is somewhere down here. I can't really tell where it is. It's below the numbers. Okay, this one is a little bit better. It's kind of down here. Still not too easy. This one, probably your best measurement. Okay, it's right in the middle of your 10 mil graduated cylinder. It's going to give you the best measurement. And this one, obviously, absolutely not. You can't even tell where the 5 is on there. How do we need to measure something? I can look at this nail right here, and I put this nail up to here, and I say, I think it is 6 centimeters. Okay. 6 centimeters is right, it is 6 centimeters, but it's not a very good number. I can make that number better. If I actually look at where this number falls, 6, 1, 2, 3, I can call it 6.3 centimeters. And that's a better, more precise measurement. But I can get even better than that because I know for sure it's 3. These are both called certain. I know both of them for certain, both of these digits. I always want to measure to an uncertain value. That's what I highlighted up here in red. I always need to estimate an uncertainty. So if I look at where it actually falls, it's really above the 3 but below the 4. Now this is where it's uncertain. Is it really 6.3 or is it 6.34, 6.33? I don't know for sure. This is where you get to decide which one you think it really is. and that's what you put down. This is the uncertain digit. And all your measurements for all of your labs for the entire year should always include an uncertain digit. It gives us a more precise measurement, and when we talked about significant figures, it tells us more information. Another example. Let's say I was reading this graduated cylinder. What's my measurement? Well, I know it's above the 78, and I know it's below the 79. So I could call this 78, but I want it to be more precise. So my uncertainty is, well, it's probably maybe 78.7, let's say. I can tell it's above halfway. Halfway might be about there, but it's above that, below the 79. And that's not a bad number. But if I have the ability, and I have the markings on there, I need to be give better readings out. So if I actually had these markings here, I could actually go, this is 78 point, and I count 1, 2, 3, 4, 5, 6, 7, 8. It's above the 7, below the 8. So I would call that 7, maybe 7, 8 mils. Okay, that's a more precise measurement. And when I'm given these numbers, I need to include it as this is the 8 is my uncertain. So I'm always going to measure things to the uncertain digit and always record them. Now, why that's important is because we have what's called significant figures. In science, we need to know what we really do know. So if I really do know that 8, I need to include it. If I really do know that 7, I need to include it. And when we start doing calculations is where it starts to get really important. I want to give you the rules for determining the significant digits first, and in class tomorrow we'll start learning how to use them in calculations. So some rules, again, pause this, write this down. You need to have this memorized for the test. And I'm going to make a note of that. So memorize these rules for the test. You have to know them. Non-zero digits are always significant. So if I'm given a number of 3.44, this has 3 sig figs in it. They're all the numbers count. This next one, the 199476, all count as significant. It has 6 significant digits. Okay? That's not too hard. What gets tricky is when we start talking about zeros, because zeros sometimes are and sometimes aren't significant. So our first rule, again, you need to make sure you memorize all of these rules. If the zero is what's called between two non-zero, or sometimes I call these counting numbers, counting digits, it is significant. So between is significant. So my examples, these zeros all count. 1, 2, 3, 4, 5, 6. This one has 6 significant digits. Even if I have a decimal place, like this one, 4.05, there's a decimal place, there's a 5 after it, it's still between. It is significant. Next rule, if you have a 0 in front of non-zero digits. So in front of is not. Okay? And that's when we have our decimal places. These are just placeholders that push the number out. Okay? So something like 0.00065, these don't count for significance. I still have to report them. It has 2 significant digits. The next one over here, 0 is not significant. 901, this one is between. So this 0 right here is significant. It has 3 significant digits. Okay, fourth rule. If it is at the end, it depends if there is a decimal, because if there's a decimal, it is significant. No decimal, it is not. So no decimal equals not significant. Okay, examples. The first one, 150, there's no decimal here. which means this one doesn't count. So the 150, this one is not significant. You have two significant digits. Now, I still have to report the 0. It's a placeholder. If I went to work and earned $150 that day, I would be kind of upset if my boss paid me $15 and said the 0 is not significant. The 0 is still important because it's a placeholder, but it is not significant. It means it wasn't not measured to that accuracy. In this case, the next one, the 150 with the decimal means that 0 is significant. That was measured to 150 exactly. You put it on the scale, it was 150 exactly. This next one down here, 41.680, it has a decimal, which means they're all significant. 5 sig figs. This next one, 40.0, I see a decimal, therefore whether it's before or after the decimal, it's after counting number and it includes a decimal, they're all significant. Okay. When we talk about things that are counted, infinite means infinity and beyond. Okay, think about Toy Story. It goes to infinity and beyond. If it is counted, it is infinitely significant. So how many jelly beans? I have 1, 2, 3, 4, 5, 6, 7, 8. 8 jelly beans. Okay. Report with significant digits. I could say 8.0000000, and I could keep going on. If I try to do a calculation with jelly beans, how much does 8 jelly beans weigh? The 8 does not count as something I have to look at for significance because it is infinitely significant. Also, conversion factors are assumed to have infinite significance. Again, this becomes very important when I'm doing my calculations. If I am trying to convert from centimeters to inches, that 2.54 is infinitely significant. So if I know it to 4 significant digits, I'm going to continue using the 4 than my measured value, not my conversion factor. And we'll talk about that more when we talk about conversion factors or calculations. But something like this has infinite significance, not 1 because of the zeros and no decimal. Consider infinite significance because it's a conversion factor.